Hello there, you're listening to the Science of Everything podcast, episode 24, Vibrations and Waves, and I'm your host, James Fodor. In this episode, we're going to look at, vibrations and waves. Specifically, I'll give an overview of the basic properties of wave phenomena, including a definition of waves, a discussion of the mediums through which waves travel, and a look at wavelength, frequency, and amplitude. I'll also discuss some of the more interesting behaviours that waves can be involved in, including interference, polarization, resonance, reflection, absorption, refraction, diffraction, and also standing waves. This episode will sort of be the basis for future episodes that I plan to do on sound and light, which require some basic understanding of wave phenomena. So if some of this is a bit theoretical, bear with me because you'll need this background for later episodes. Plus, it can also be quite helpful to understand these wave terms more generally because they come up quite often in sort of more scientific or even pseudoscientific discourse. Alright, so let's jump in. What is a wave? In physics, a wave refers to a disturbance that travels through time and space, or through space-time, which is accompanied by a transfer of energy. Wave is not the same thing as a vibration. Vibration is basically a single disturbance in some medium, which is propagated through it. A wave is more like an ongoing or continuous disturbance, or at least it's a broader phenomenon. So, for example, if you were to shake a string once, up and down, say you had a string connected onto some hook embedded in a wall, and you were to shake that once, that would be a vibration. But if you were to keep shaking it, or multiple vibrations traveled up and down the string, that would be a wave. So it's a little bit sort of arbitrary, the exact distinction between a vibration and wave. And when you look at the actual physical world, pretty much everything's more or less a wave, because you don't generally get single vibrations so much. Like, for example, if you throw a rock into a pond, you get waves. You can't just get sort of one vibration ripple coming out. It's going to be a wave. But anyway, that's the basic idea. A wave is sort of a broader, larger thing than just a single vibration. Or, in other words, a wave is made up of numerous repeated vibrations. Now, I've said that wave is a disturbance, so what do I mean by that? Well, exactly what a disturbance is depends on the medium in which a wave is traveling. Now, the medium, or the transmission medium, is the material substance through which waves are propagated. Mediums can include air, or water, or wood, really any material substance that can, through which vibrations that form the wave can propagate. The way a wave works is that we'll call it a molecule, but it could be an atom or even larger than that, but for the moment we'll call it a molecule. One molecule sort of vibrates, maybe up and down, backwards and forwards, whatever, and then that molecule, that vibration in the molecule in turn causes a vibration in another molecule, perhaps to the left or to the right of the first molecule, which then causes the second molecule to vibrate in a similar way, which then causes a third molecule to vibrate, and so on. So in that sense, the energy, the vibration energy, or the energy of motion, is passed along from one molecule or one atom or one whatever to the next one, and thereby the energy travels through the medium. But the key thing about a wave is that no matter is actually transferred in the process of of moving the wave. So, for example, if you have a water wave, go back to our example of throwing a rock in a pond. When you see those ripples move outwards from the center where the rock fell in, water is not actually moving. Water molecules or masses of water are not actually moving from the place where the rock fell outwards towards the edge of the pond, unless you're doing something else. But just the wave itself will not move water from the center outwards. All that's happening is energy is moving from the center outwards in the form of those waves, which in turn essentially are formed of vibrations of water molecules vibrating up and down, or which, well, in this case it's up and down essentially, and then passing that energy on to the next water molecule, to the next water molecule, to the next water molecule, and so on. And so the energy is transferred, but no matter is actually transferred. And as I said, the medium is the material substance that transmits the vibrations across space. Often when describing waves, you'll talk about them as either on a string or in water, because they're familiar examples that we can relate to, but waves is more of an abstract idea. When I talk about a medium, this applies, for example, even to light waves or to other type of electromagnetic radiation waves. So sometimes the medium, or exactly what we mean by vibration, or exactly what is doing the vibrating, is not so obvious, but we still apply the basic framework to it. So, for example, a Mexican wave where one person stands up in a crowd and waves, and then the person next to them stands up, and so on, and that moves through the stadium. That is a wave, and the energy that we're talking about is essentially the energy of motion of the people moving up and down. But no people actually move across the stadium. It's only the wave, or the energy in some sense, that moves. And in that case, the medium would be the people, or the spectators in the stadium, and the vibrations really consist of the individual things that are vibrating are really just people standing up and down. So that's a more abstract example of what a wave is. Other examples of waves include, as I've already said, water waves on the ocean, sound waves in the air, radio waves, microwaves used in microwave ovens, light waves emitted by the sun or lights. Waves are very, very common in nature. I've already mentioned electromagnetism, of which light is an important subset, and sound, two very important waves. and very common in nature. So that's why it's very important to get this sort of basic understanding of them, and how we can describe them, and so on, how we can understand their behavior. Okay, before we leave the basics, I just want to talk about the two different types of waves. Remember that there's different media in which wave can travel. We've covered that. That's the water waves, the sound waves, and so on. But all of those can be classified into two broad categories of waves: the transverse waves and the longitudinal waves. A transverse wave is basically where the direction of travel of the wave itself, or the direction in which the energy is moving, is perpendicular to the direction of vibration of the individual molecules. And light wave would be an example of this, or light waves would be an example of this. Also, water waves would be another one. Basically, the light waves, or probably water waves is an easy one to visualize. At least ocean waves on the surface of the water. The water molecules go up and down, but the wave itself is traveling along the surface of the water. So the directions of motion are perpendicular to each other. That's also a wave on a string would be an example of that. Remember that string connected to the wall by a hook? The string, the parts of the string that are waving go up and down, but the wave itself travels back and forth along the string. So that's another example of a transverse wave. Longitudinal wave is where the direction of vibration of the individual components and the direction of travel of the energy both are in the same direction, or at least in the same plane. So sound waves is an example of that. The air molecules move backwards and forwards in the same direction that sound is traveling towards us or away from us. They don't sort of go up and down and the sound travels forwards and backwards. It's in the same direction, or same axis in a sense. So these two different types of waves, transverse and longitudinal, can have somewhat different behaviors in some circumstances. So that's the basics of what are waves and wave media and how they travel. Now let's talk about how waves can be described in a bit more detail. As I said, waves are a broad phenomena, and they can differ depending on whether they're transverse or longitudinal, and also depending on what medium they travel through. But even giving those things constant, so let's just pick transverse waves in water, or just longitudinal waves in air. Holding those two things constant, there are still many different ways in which waves can vary. Probably the four most important properties I'm going to talk about are amplitude, period, wavelength, and frequency. And these are quite closely related to each other, particularly the last three. But just before I get onto those, I'll talk about the concept of sinusoidal waves. Hopefully, those of you listening have at least some background in mathematics, even just like early high school would be sufficient. If you remember those sine or cos waves, some of you may be quite proficient in mathematics, I don't really know. But anyway, you remember sine or cos waves, or sine or cos graph, sine or cos function, trigonometry. They're basically that graph that kind of goes up and down and repeats on forever. It's a smooth curve that continues to go up and down onwards. And basically sine and cosine, or sine and cos, they have the same shape, that one's just shifted horizontally relative to the other. But hopefully you can picture what I'm talking about. If not, look up cos graph on Google Images or whatever and just see that shape. That shape is what we use in physics, well, in actually most of science really, to describe the behavior of waves, because it turns out that even though theoretically waves can have any shape, they're just vibrations. So you could have a sawtooth wave, for example, where effectively you just go diagonally up and then a sharp break diagonally down, diagonally up, diagonally down, just like the tooth of a saw, the straight tooth of a saw. Theoretically, that could be a wave shape, and waves like that can occur, but most of the waves that we actually find in nature and that we want to describe are sinusoidal in shape, so they essentially look like that sine and cos graph that we talked about, or at least could be described in those terms. If not a single sine or cos graph, then we can actually include multiple sine or cos waves and sort of superimpose them on one another and create more complicated waves. And I'll talk about that in more detail, but I just want you to understand the basic point that the amplitude, period, and stuff that I'm going to talk about now apply most specifically to sinusoidal waves, sine and cos wave, basically. But that in turn can be used to describe pretty much all the waves that actually exist. So from now on, sort of when you think of wave, think specifically of that sinusoidal shape. And just remember that sinusoidal shape, first of all, is very common in itself, and second of all, can be combined or sort of altered in a way that it can be applied more generally even to cases where it doesn't apply. So it's a very useful basic model to understand. Okay, so taking that basic sine cos graph shape, the sinusoidal wave, I'll now talk about its four key properties: amplitude, period, wavelength, and frequency. Amplitude just refers to the distance between the mean value of whatever is oscillating, so in this case the mean value of the graph, in the default case it's 0, the distance between there and the maximum or minimum positions that the wave gets to, or in this case the graph gets to. So basically, the sine curve just goes up and then turns and comes down and then up and then down, and it continually moves up and down with a mean of 0. The distance between 0 and either the top, the maximum, or the minimum value that the graph gets to, that is the amplitude. Now be careful here. It's the distance between the middle, or the median, and the top, or the bottom. Those will be the same because it's symmetrical. Not the distance from the top to the bottom. The full distance from the top to the bottom is twice the amplitude. And Generally speaking, the amplitude kind of represents the power or the energy that's in the wave, although that doesn't work perfectly because it depends on exactly whether we're talking about a sound wave or whatever, but that's kind of the basic idea. So the higher the amplitude, the more sort of power there's in the wave in some generic sense. Don't take that power word too literally, but just as a broad idea. Next, period. The period is the time interval between each oscillating variable, or each particle, or whatever we want to call them, returning to any particular state following a full wave cycle. So imagine a water molecule on the surface of the ocean or a pond, wherever. The vibration comes along, so it starts going up, and then it reaches its maximum. That's the top of the amplitude. Then it starts going down again. It returns to the median point where it started, but now it's going down, so it continues below the median point, reaches the minimum point, and then comes back up again. And now it's at where it was originally, traveling in the same direction. It's traveling up. Say it started traveling up, just for the sake of argument. So basically, it went up and came down, then went down and came up again. That's a full cycle of the wave. The time that it took for that oscillating variable, in this case the particle, or it could be an air molecule or whatever, the time it took for that to happen is the period. The shorter the period, the quicker each molecule or each variable, whatever's moving, returns to its initial position. So to take our maximum wave example in the stadium, the period could represent the time period between one person standing up, sitting down, and standing up again. Obviously, the shorter the period, essentially the more rapidly the wave is traveling, although there are other variables as well. Next is the wavelength. The wavelength refers to the distance over which the wave repeats, or the distance traveled by the wave in a single period. So remember I said that period, wavelength, and frequency are kind of closely related to each other, and speed as well. So a period is, remember, the time interval between a particle being in the given position and then the particle being in the same position going in the same direction the next time after one wave cycle. That's the period. The wavelength is the sort of the horizontal distance, or the distance traveled by the wave during that time. So for example, return to our water molecule analogy. The water molecule goes up, comes down, and then returns to its initial position, goes up a bit again. That takes a certain amount of time. During that amount of time, the wave has traveled a certain distance, a certain horizontal distance in this case. That distance is one wavelength. It's really much easier to see this if you just look at a graph. Just type in like sine graph or something like that, or sine wavelength period, something like that. You'll find a labeled graph that has all these things on it. It makes it much easier to see than me trying to explain it. Next, frequency. Frequency is the inverse of the wavelength. So that is, we take 1 and divide it by the wavelength, and that gives us the frequency, which is frequency is 1 over wavelength and vice versa. So frequency and wavelength are they're proportional to each other, directly proportional to each other. So the higher the wavelength, the lower the frequency, and vice versa. So translated into sort of words, if the wavelength is the distance traveled by the wave in one period, the frequency is the number of oscillations per unit of time. The inverse of that, or the flip side you might say, is that the frequency is the number of oscillations per unit of time that occur, or the number of wave cycles that occur per a unit of time. So they're directly related to each other, wavelength and frequency. And finally, the speed. Speed is just defined as distance over time, as hopefully you should know. So generically, speed is distance over time. That's just the definition, or the distance traveled over the time taken to travel that distance. That's just the definition of speed, or velocity. In the case of wave, though, the distance traveled in one time period is the wavelength, and that time period is going to be the period. So basically, velocity is going to equal distance over time, which in the case of a wave is wavelength over period. So imagine v equals lambda over t. Lambda being the normal symbol for wavelength, or if it makes it easier for you, v equals w over t, t representing time, which is sort of the period. However, given that frequency is the inverse of period, that is, frequency is 1 over period, 1 over t, we can rewrite that equation, v equals lambda over t, as v equals lambda times f, because f is just 1 over t. The frequency is 1 over the period, just as we defined it before. So that's just another way of saying that the velocity of a wave is equal to the wavelength times the frequency, or basically the distance traveled by the wave in a given period multiplied by the number of periods per unit of time. If you want to work out the velocity of the wave, you work out how far the wave travels in each wave cycle, or over each period, and then you work out how many periods there are in a unit of time, say in a second or minute, whatever. So distance for each cycle, number of cycles per unit of time, that gives you the speed or velocity of the wave. That may be a little bit confusing. You may want to sort of look at those equations. It's a pretty simple equation, but look at it written down. But the speed of a wave, by the way, depends upon the medium through which it is traveling and how rapidly or how easily the objects in the medium can vibrate in relation to each other and so on. But anyway, so just to recap, because these concepts are very important. Amplitude, distance from the medium wave value to the maximum or minimum points. The distance between the maximum and the minimum is twice the amplitude. Period is the time interval between a single particle going through one full wave cycle and returning to its initial state. Wavelength is the distance traveled by the wave during a single period. Frequency is the number of oscillations at the wave, or what number of wave cycles per unit of time, and the speed of the wave is equal to the wavelength divided by the period, or, which is the same thing, the wavelength times the frequency. Okay, so hopefully that wasn't too confusing. But those 4 or 5 fundamental concepts are very important to understanding what comes later. Okay, I just want to have a brief word on pendulums now. Often if you read a textbook or other treatments of waves, they'll sort of belabor pendulums because they're kind of interesting, but I don't want to focus on them too much here. Basically, a pendulum is just a weight suspended from a pivot so that it can swing freely. So, for example, if you can imagine a grandfather clock, they have those, pendulums hanging down from them that rock from side to side. That's a pendulum. Or basically, if you just have a yo-yo and fix the length of the string so that it doesn't keep on rolling, and sort of swing it backwards and forwards, that's a pendulum. Pendulums are an example of wave motion, especially if you represent, for example, the distance of the weight from either its horizontal position or its vertical position. Either way, it doesn't really matter. You can graph that and you'll get essentially a sinusoidal function. The interesting thing about pendulums is that the size of the swing of the pendulum doesn't actually matter. So in this case, when I say the size of the swing, that's referring to the amplitude. So imagine that we're graphing the pendulum. Imagine we've got this a sine graph, and on the vertical axis, on the y-axis, we've got we're plotting the distance. Let's say the horizontal distance of the pendulum. So the horizontal distance to the left or to the right of the straight down vertical line in the middle of the clock. Let's say. So that's on the y-axis. When it's up, it's to the right, and when it's so when it's positive, that means the pendulum's to the right, to our right of the middle point. When the y value is negative, that means the pendulum is to the left. The further it is to the left, the further down it is on the y-axis. The further the pendulum is to the right, the higher it is, the larger the value on the y-axis of this imaginary graph. And x-axis will just represent time. So in this case, the further you pull the pendulum to one side or the other to set it off, the higher the value of the y-axis will be. So the higher the value will be on the y-axis that you start with, and then it goes down and it will go down to a larger y value, a larger negative y value, and then so on. So basically the y values will be larger, and that translates to a higher a higher amplitude, because remember, the amplitude is just the difference between the maximum and the middle point of the graph, or between the middle point and the minimum point of the graph. So the long and short of it is the amplitude of a pendulum does not affect its period or the swing time, and that is why pendulums, for example, as used in grandfather clocks, are so useful for timekeeping, because it doesn't matter. So say you start the pendulum swinging and then let it go. Obviously, it's going to the swings are going to get smaller and smaller over time, essentially because there's a bit of friction occurring there in the wood or in the internal mechanism of the clock and so on, and with the air molecules too. So there's a bit of friction there. That's diminishing the energy, pulling the energy, and so gradually it'll stop swinging. However, gradually the pendulum will stop swinging. However, in the interim, as it continues swinging, so it gets the swing gets shorter and shorter, smaller and smaller. In other words, the amplitude gets smaller and smaller, but the period, the time for one swing to occur, doesn't change, and so you can just keep measuring the number of periods that have occurred, and then track time in that way. All clocks essentially work by counting vibrations or by counting periods of some repeated motion. For example, electronic clocks just basically calculate the changes in polarity in an electric circuit. We haven't done electronics, but we'll do that in a future podcast. But basically, that's how clocks work. Even if we just use a solar clock, essentially we're just counting the number of periods that have occurred with the sun rising and setting and so on. Okay, so now I want to start talking about some of the more interesting wave phenomenon, and we'll start with interference. Interference is a fairly simple principle. It basically states that if you have two waves in the same place at the same time, so let's say two water waves on top of each other, they interfere with each other. So they're not just independent of each other. If you had two physical objects, say two cars in the same position at the same time, that's either impossible or they'd crash or whatever, however you're going to arrange that exactly. But that's not the case with waves. Basically, they just add up. You just add them up. So, for example, if two waves are on top of each other, so that their maximum points line up, so they're basically their positive amplitudes in the same position and their negative troughs are in the same position, then they'll just amplify each other, so that the height is even greater of the final combined wave, and the trough or the depth is even lower. The middle points will of course be the same, because 0 plus 0 is still 0, but you essentially add the amplitudes and to make the amplitude of the final wave that much bigger. That would be an example of what we call constructive interference. Basically, two waves sit on top of each other so that they add up and increase the amplitudes of the final wave. A second type of interference is destructive interference, where essentially the peak of one wave overlaps with the trough or lower point of another wave. And so if the amplitudes of those initial two waves were the same, so say there were 5 in both cases, but if a trough of one of the waves overlaps with a peak of the other wave, then essentially you've got +5 plus -5, which adds to 0, or regardless of whatever the amplitude is. If the amplitude of the two waves is the same, they'll cancel out completely, and so you'll actually get nothing there. So it's possible to combine two waves together, and because of interference, you can get nothing there. You won't see anything. This is actually interesting. So if you can do this on a string, for example, you put one vibration which goes in one direction. So say it's moving along the wave, so pointing upwards, moving along the string pointing upwards, and then you do another one from the other direction, but with the vibration or the wave sort of pointing downwards. The two will move across each other, and when they reach the middle, when they reach each other, they'll line up, and they'll actually completely cancel out. It'll look like the string isn't moving at all for a second or so there, and then they'll emerge from the other side, and the two waves will still be there again. So it's very interesting how that works, and that's essentially part of the sort of representative of the fact that there's no matter moving here. It's all about moving of energy. We need to maintain conservation of energy, but -5 plus +5 is 0, so we can sort of go from that 0 energy to then having the energy there again. So interference is a very important concept to understand, and also understand that interference doesn't have to be all or nothing. It doesn't have to be, either the wavelength, the amplitude doubles, or they completely cancel out. It could be a partial cancelling out. So if you have a small wave which partly cancels out a big wave, then the final wave, the superposition of the two waves has a smaller amplitude than it started with. By the way, interference only changes the amplitudes of waves. It doesn't affect the period, or it doesn't affect the wavelength. Those are all the same. It's just the amplitude that it'll change. Okay, so that's interference. Second thing I want to talk about is phase. This is a little bit more complicated if it wasn't complicated enough already. Phase refers to the fraction of a wave cycle that has elapsed relative to an arbitrary point on the wave. Okay, that probably doesn't make any sense. A more useful way of looking at phase is to consider phase difference between 2 points on a wave. Basically, phase difference refers to the sort of difference in position, or difference in direction as well, direction of travel, of 2 points on two waves, or the same wave, having the same frequency and referenced at the same point in time. Now, the key thing that we want to understand here is really whether waves are in phase or out of phase with each other. You actually hear this, well, if you watch science fiction or even just generic shows. They might talk about something being in or out of phase. It's particularly common to explain why someone's turned invisible or can pass through walls or something like that. They're out of phase. This doesn't really mean anything in those contexts. But what the term in phase or out of phase means is essentially how similar the two waves, because you can talk about 2 points on a single wave or two different waves, but let's just take 2 separate waves to be a simpler case. If the 2 waves are in phase, it means they have the same frequency and are aligned relative to each other so that they interfere constructively. So imagine we have two waves here, just one wavelength basically of the sine graph. Imagine we have that except times 2. The only way for those 2 waves to be in phase is if they have the same frequency, so there's the same length basically, and that when you put them in the same place, they are aligned so that they interfere constructively, so peak to peak and trough to trough. If they are slightly offset so that the peaks almost match up but not quite, or indeed completely offset so that peak lines up with trough and vice versa, then they are not in phase, they're out of phase. And in fact, that's where the concept of phase difference comes in, because the closer they are to being in phase, essentially the lower the phase difference is. If phase difference is exactly 0, then they're precisely in phase. The greater the phase difference is, the further away they are from being completely in phase. And remember, you have to be the same frequency, or same wavelength, obviously those are related as we talked about, and aligned properly. So if you're aligned properly, you might have one peak and trough that overlap each other properly. But if the waves are different, if the 2 waves you've got a different wavelengths or different frequencies, then the next peak will not be in the same position for the 2 waves, because wavelengths essentially refers to the distance between one peak and the next. And if one wave has a larger wavelength than the other, then even if peak 1 of each wave are in the same position, peak 2 of the 2 different waves will not be in the same position, because one will be closer to the initial peak than the other one, and so that the second peaks will not line up, and so therefore the 2 waves are not in phase. Similarly, even if you have the same frequency, you still have to be aligned properly so that your peaks line up to your peaks and your troughs line up to your troughs. So being in phase is a fairly strict criterion. Phase difference, or the concept of being in or out of phase, is important, for example, in laser light, because when light is in phase with itself, or when multiple sort of photons of light are in phase, then it increases the intensity of the light. we'll talk more about that later. If light's out of phase or if waves are out of phase with each other, the behavior of the wave, the superposition still occurs, by the way, regardless of where you, or interference, it still occurs regardless of whether you're in phase or out of phase. However, the behavior of the interference patterns will be much more complicated if we're out of phase, especially if you have different frequencies, because sometimes the peaks will line up, sometimes the troughs will line up, sometimes there'll be some combination, and the resultant combination will be very complicated. But in no case do they become invisible or waves just don't interact with each other or something weird like that. Okay, so that's phase. Now I'm going to talk about polarization. Polarization has some similarities to phase in that it relates to alignment, but it's a bit different. Firstly, polarization only is relevant to transverse waves, so longitudinal waves don't have a concept of polarization. Secondly, it refers not to the orientation of, say, peak relative to peak or trough relative to trough, or nor does it relate to the frequency of the wave. It essentially relates to the sort of rotational orientation, if you want to think of it like that. Basically, if you think about it as, remember, I said this is a transverse wave, so think about this sine cos graph that we've got. It goes up and down. But then imagine we've got a second one. Suppose it has the same frequency. It doesn't actually matter. It can be polarized without having the same frequency or wavelength. But suppose it has the same frequency just for simplicity. But then imagine we've sort of rotated it, not on the y-axis or on the x-axis in the normal ones in the graph, but in the z-axis, so in the third dimension. So sort of imagine that we pick up, or we grab hold of the top of the sine graph and sort of pull it towards us, imagining it was in 3 dimensions, and we sort of rotate it towards us, and so that the peak sort of tips down a bit, and the trough also sort of move up the other side. It's sort of like rotating a wheel around in a sense. Hopefully you can imagine what I'm talking about. Now that new wave that we've created by that rotation in the z-axis, in the axis sort of in and out of the page or in and out of the screen, if you want to think of it like that. That rotation has made the second wave no longer polarized, or no longer of the same polarization as the first. In order to be polarized, the alignment of the direction of vibration of the transverse waves must be in the same direction. So, for example, this sine wave that we've talked about, the x-axes of these graphs still line up perfectly. We haven't actually changed that. We've just rotated around the x-axis. We haven't moved it or changed its orientation. So the x-axis is still the same, which means that the direction of travel of the wave itself is identical. That hasn't changed. So if we're talking about light, the light waves are still traveling exactly the same direction. The difference is we've sort of rotated the light wave so that one is sort of at an angle to the other one, not in terms of the direction they're traveling, but in terms of the direction that we'll say, photons are vibrating. So in one case, the photons might be vibrating up and down, but in the second case, the rotated version, maybe they're vibrating on an angle diagonally or something. In those two cases, the waves are not polarized because the direction of vibration of the molecules or the medium or whatever in the two cases is different. Even though the wave is traveling in the same direction, the vibration's not in the same direction, and so they're not polarized. You can see why this is only relevant to transverse waves, because longitudinal waves don't have the direction of vibration in longitudinal waves is the same as the direction of travel. So this concept of sort of rotating one relative to the other doesn't apply. An application of polarization is basically in polarized sunglasses, because what they do in these sort of sunglasses is they put lenses in them which keep out light of a certain polarization. So light waves basically have a certain orientation, but not light waves of a different orientation. And it turns out that reflected sunlight, say from shiny metallic surfaces or from water, tends to have a different polarization on average than light that comes to us directly from non-shiny surfaces or just from the sun or from the sky or wherever. So effectively you can selectively block out the reflected light compared to light reflected from shiny metallic surfaces and water and stuff like that. You can selectively block that out and allow other light in. That's how polarized sunglasses, for example, can reduce glare. Okay, that's polarization. Now I want to talk about resonance. This is another thing that you might have heard before. In fact, the concept of resonance is mentioned rather a lot in popular discourse, I find. Also, people use the word like one thing resonating with another thing, or I resonated with her, or whatever. But I don't think too many people really know what that means. Basic idea behind resonance is that things are vibrating together. They're vibrating sort of in step with each other. And so in a sense they complement each other rather than working cross purposes. That's the basic idea behind resonance. And that kind of works, that's how people use the word in sort of a popular discourse. It's also kind of how the concept is used in physics as well, but obviously it's much more precise than that. So I'm going to go into more detail now about what resonance actually means. Every object or system has a natural frequency, which is the frequency at which it tends naturally to vibrate when it's struck or disturbed or knocked in some way. Basically, this natural frequency is determined by the properties of the object, like mass and length and stiffness and other things like that, and viscosity and whatever else. So when I'm talking about an object or system, I'm talking about an atom, a molecule, a DNA molecule, a cell, a laptop, whatever. All of these things will have some kind of natural frequency. You can get them to vibrate at different frequencies, but you have to put a lot more energy into them than if you just get them to vibrate normally. And you can easily see this by filling up glasses of water or bottles of water to different levels, and then striking them with a spoon or something. You'll see that the sounds that you get are different pitches, which represents different frequencies at which they're vibrating. And if you strike them in this exact same way, and they'll vibrate at different frequencies because they have different masses and therefore different natural frequencies. Now, resonance refers to the phenomenon whereby periodic application of small amounts of force at or near the system's natural frequency over time greatly increases the amplitude of vibration. So the analogy that's always used with resonance is the example of a child on a swing. So the natural frequency, in a sense, of the child on the swing is that the sort of natural time based on gravity and the child's mass and so on that it takes for them to swing forward and then come down and back to, say behind the swing where the parent's standing pushing them. So that's the frequency, or I guess we'd say that the frequency would be the number of times they do that in a minute or whatever. The number of swings they make in a minute. That will differ between child, but for a child it's going to be basically the same. Now when you're pushing them, basically you're going to want to push them either once per swing, or once every 2 swings, or once every three swings, some whole multiple of the period basically. But you're not going to want to push them every 3/4 of a cycle or every third cycle, because if you do that, basically what happens is sometimes you're going to be pushing them when they're or for example, take the 3/4 example. The first time you push them when they're right in front of you, which is where you normally push them, but then the next time you push them when they're sort of halfway back down coming towards you, then the next time you push them sort of halfway when they're going away from you, and then the third time you push them again when they're down right in front of you. So you're pushing them at different times. Clearly, if you did that, it would become a mess, because sometimes you're pushing them when they're going away from you, sometimes you're pushing them when they're coming towards you, sometimes you're pushing them when they're sort of just halfway in between. So sometimes the energy adds to the energy that they already have, adds to the motion that the child already has. Sometimes it subtracts from it, and it kind of gets in a mess. Basically, if you're trying to do that, you just get into a chaotic motion, and motion will either die out or will just kind of not really go anywhere. And it becomes very hard to maintain that sort of motion. That would be non-resonant addition of force. So you can do that. You can push them in those intervals if you wanted to, but that's not resonance. Your energy wouldn't be resonating with the natural frequency, and therefore you're not going to really get anywhere. What resonance does is that it only applies the forces basically in time with the natural frequency at which it's vibrating. So in this case, it's only pushing the child when they're right in front of you, when they're swung back towards you, just ready to be pushed again, in a sense. Whole multiples of that. If you push whole multiples, say every 2nd swing or every 10th swing, the less frequently you do it, the less energy is going to be added. However, as long as you do it at a whole multiple of the frequency, you'll still maintain that resonant motion. You won't get the chaotic motion that would happen if you did it every 3rd period or something. And basically, when you do that, when you add the energy only on those sort of frequency intervals in line with the natural frequency, the amplitude will gradually increase. Not forever, because there's friction, for example, regardless of what the system is. There's always some kind of friction. Second law of thermodynamics. There's some kind of loss of energy. So eventually you'll reach an equilibrium where the amount of energy you're putting in is equal to the amount of energy that's leaving, and so the system will reach a steady state there. But up until that point, you'll gradually increase the energy. So there's an example you may have heard of a bridge that collapsed because of essentially wind which was blowing in some complicated way on the bridge in line with its natural vibration frequency. So that although the force of the wind wasn't actually very strong, it was gusting in such a way, or maybe it was the waves or something. I can't exactly remember what the story is, but I think it was the wind. It was gusting in such a way, blowing in such a way that it was adding energy in line with the natural frequency of the bridge, and so the bridge started swaying or vibrating only a small amount, but it gradually built up over time as that energy was added in a sort of consistent way in resonance with the natural frequency of the bridge, and the amplitudes of the vibration of the bridge got larger and larger until the bridge tore itself apart and collapsed. Now, I looked this up, and it seems that the actual case is a bit more complicated than that, and there were more complicated physics going on. I don't really care exactly about that. I'm just trying to illustrate the point of what resonance can do. Resonance can indeed make things happen, or sort of store energy in a way that's not possible if you just add the energy in at sort of random intervals. Another example of that would perhaps be on a seesaw. One person needs to push up at the right time relative to the other person. If each person just pushes at random times, you're not going to get a nice coherent motion there. You're not going to get very high either. Pedaling a bicycle might also be an example. You need to push the pedals down at the right times. If you just do it at random times, you're not going to get the resonance in, you're not going to get the speed up in the wheels there, and the bicycle's not really going to go anywhere. So resonance is a very important concept. But fundamentally, it refers to adding energy into a system consistent with, or basically at the same time as, its fundamental frequency, or at least whole multiples of that. Alright, that was resonance. Now I want to talk about reflection. This one's, compared to polarization, phase, and resonance, this one's actually quite simple. Well, really, reflection and absorption, I'll take these two together because they kind of go together. Reflection basically refers to the fact that when a wave hits a barrier, or more accurately, a boundary between two different media, so for example, it could be air moving to a sound wave hitting a wall, or a sound wave moving from water to air, or electromagnetism moving from air to water, or from brick to air, or whatever, but any change of medium like that. Some of the wave will be reflected, so it will essentially bounce off and pass and travel back in the direction it came from, and some of the wave will be transmitted through the medium, so we'll keep going through it, and some of the wave energy will be absorbed by the new medium that it's traveling in. Really, all mediums will absorb some of the energy. This is basically just the friction that I was talking about internal to the medium. So, for example, water molecules rubbing up against each other, or air molecules bouncing off against each other in ways that are not consistent with the overall wave motion. That will sort of leak energy away from the wave itself, and therefore gradually diminish amplitude over time. That's why sound actually travels very well in water, because water has a very low viscosity, and that's very important to not essentially leaking away energy. So water will travel actually hundreds of kilometers through water, if even thousands really, if it's loud enough and it's not disrupted by something. So that's the absorption aspect. Reflection occurs, as I said, when the wave moves across the boundary from going from one medium to another. And essentially the reason it happens is because different mediums will be differently conducive, or conducive to different degrees, to the transference of that wave. So for example, sound waves travel more or less easily in water compared to air, or compared to brick, or wood, or whatever. And so when that energy is approaching the boundary, or when it reaches the boundary, the energy, the vibrations, will essentially just travel in the path of least resistance, just like water running downhill or whatever. Some of them will continue through the wall, some of them will bounce back and continue through the edges, depending on which is easier. If it's much easier to travel through air than it is through brick, as indeed it is for sound waves, or most sound waves, then most of the energy will bounce back and will push the molecules sort of back in the opposite direction they came from, and then the wave propagates back in the direction it came from. That's basically an echo. But a small amount will travel through the brick, and the sound is transmitted through the brick. If you have air and water, sound travels much better in water than it does in brick, so less of the energy will reflect back, and more of it will be transmitted through into the new medium. So that's basically really all that affects I shouldn't say that. That's one of the two important properties that determines how much reflection, how much of the wave is reflected. It's the relative properties, or the relative ease with which the wave can travel through the two mediums. Now I want to move on and talk about refraction. Now don't get confused, refraction is not the same as reflection. They're quite different to each other, although they're sort of related. So refraction and reflection is bouncing off. Refraction is the change in direction of a wave due to a change in its speed when a wave changes from one medium to another. So for example, if a wave is traveling from air into water, that's changing medium. Water waves travel, it could be a sound wave or a light wave, doesn't really matter in this case, but they'll travel at different speeds in the two different mediums, and so as it changes speed, it also changes direction when it passes from one medium to the other. However, refraction does not always occur. It only occurs when the wave strikes the division, or strikes the boundary between the two mediums at an angle, not 90 degrees or 0 degrees, but at some angle in between those, so at a 45 degree angle or 20 degree angle or something. Now, the best way to understand why this happens is just to look at a picture or diagram, but essentially imagine a squad of soldiers marching abreast, and they're all holding each other's hands or whatever, so that they're all connected and they're all marching shoulder to shoulder next to each other at a slight angle, or at some angle to a boundary. And say this boundary, say they're walking through grass, and they're about to emerge onto a paved area. And you can move, let's say, long grass to a pavement area. And so once the soldier gets onto the paved area, they'll be able to walk faster than they were walking on the grass. And so, but because the line of soldiers, the squad of soldiers, is traveling at an angle relative to the boundary, one soldier at whichever end, depending on which way it's angled, one soldier will reach the paved area before all the others, and so they'll start walking more quickly before the others start walking more quickly. And then the second guy, and then as the squad moves a bit further forward, the second soldier reaches the paved area, and then they start moving more quickly. But there's still a bunch of the rest of the squad that haven't reached it yet. And so by the time the final soldier reaches the paved area, all of the other ones have been traveling at that faster speed for a while already, and the very first guy who reached the paved area has been traveling at that faster speed for substantially longer than he had, than the final guy has. That sounds kind of obvious, and it is, when the soldiers are connected, sort of holding hands or abreast to each other in the way that we said they were, essentially representing a wavefront, when you have that and have the changing speeds, as we said, changing speeds at different times because of the angle, you get a change in direction of the wave. There's really no way I can explain this other than just to say look at a picture and that's what happens. And whether the degree to which the wave changes direction depends upon the difference in speeds and also the angle at which the wave hits the boundary. You can see why this only happens when there is an angle, because say that the bunch of soldiers was walking towards the boundary, suppose their direction of travel was perpendicular to the boundary, so that if you drew a line across the squad of soldiers, that line would be parallel to the boundary line. In that case, all the soldiers will reach the paved area at the same time, and so there is no difference in speed, and so there's no change in direction there. You only get that different timing of the one soldier compared to the other when there's some angle, and the greater the angle is, essentially the greater the difference in time is, and so the greater the one soldier walks compared to the other, and therefore the greater the change in direction is. Really recommend looking at an image, or even better animation of that, to get your head around how that works exactly, because it's a little bit confusing. But that's why refraction occurs. Whenever you have a wave moving across a boundary into a new medium where it travels at a different speed and it hits it at some angle, it will change direction. The greater the angle, the more the direction will change. Refraction is a very important phenomenon for light, and it's largely responsible for the phenomenon of rainbows, for example. We'll talk about that when I cover light in a future episode. One thing I just want to quickly mention, I'll bring this up in much more detail when we talk about light. This is the concept of diffraction. Diffraction basically is the spreading out of waves when it passes through a small aperture or passes around the side of a small obstacle. The obstacle has to be relatively small, and gap has to be relatively small relative to the wavelength, otherwise you don't really notice it. So technically all objects have a wavelength. I have a wavelength, your car has a wavelength. In terms of quantum physics, I think we talked about this, but the wavelength is extraordinarily small, you can't notice it. So, technically you could observe diffraction of billiard balls, but it would be ridiculously small and it wouldn't look like anything. When we talk about things as small as electrons, though, and photons, we can see the diffraction occur, and we can see the spreading out occur when we pass them through narrow slits or around small objects. But this is much more obvious if you just talk about waves in water. If you have a wave that's sort of a flat wave that's just moved down and you pass it through an aperture, it will spread out and go in a nice circle for you there. Once again, pictures of that on the internet. I won't go into detail exactly why that happens. We'll talk about that later, but it's just an important concept. I just wanted to put it in here for completeness, basically, because it kind of goes along with reflection and refraction and polarization and some of these other things. And it's an important concept, particularly in electromagnetism. One final thing that I want to talk about, and I'll go into this in more detail again when we talk about sound, because this is particularly important when it comes to sound, but this is the concept of a standing wave. This is quite counterintuitive, really. A standing wave is basically a wave that doesn't move. It stands in the same place. Now, but I've just defined wave as essentially the movement of vibrations transferring energy from one place to another, so it would seem contradictory. How can you have a stationary movement of energy? Well, basically the reason you can have a stationary movement of energy is because the energy is sort of moving, but it's moving backwards and forwards within a fixed position. And so there's no net motion. Kind of like not really like moving in a circle, more like bouncing backwards and forwards between one wall and another. It's sort of moving, but it's sort of stuck in the same place. And there's more to it than that, though, because remember the concept of interference. If you have a peak lining up with a peak, then they superimpose and you get a higher peak, or if you have a peak lining up with the trough, they cancel out. Destructive interference, and you essentially get nothing there. If you have one wave coming in one direction and another identical wave going in the other direction, so same frequency and all that, same amplitude as well, but they're just traveling in opposite directions, basically what will happen is that, first of all, at one time, the peak will line up with peak and you'll get constructive interference, and then later on they'll sort of move away from that and get to a situation where peak lines up with trough and you'll get complete cancelling out. And if you have those two waves traveling backwards and forwards, essentially bouncing between two walls or between two obstacles, bouncing like that, they're constantly interfering constructively and then destructively and then constructively and then destructively again in a fixed pattern in that way. And as I said, if they have the same frequency, it'll look like you've essentially got a string just vibrating in position. And that's what we call a standing wave. Once again, I recommend looking up an animation on this. It sounds kind of weird that you can have one wave moving in one direction and then bouncing off, and another wave moving in the other direction, bouncing off, and that they cancel each other out and produce a behavior that looks like you've just got a string vibrating there, but in fact that is exactly what happens. So it doesn't look like anything's actually moving. It just looks like the string or the medium or whatever it is vibrating. It could be air or water, but string's a good example to take from it. But in fact, you've got waves there. They're just sort of constantly constructively and then destructively interfering with each other in a regular pattern, which then produces a behavior that looks like vibration. So it's a wave that stands in position. and it's basically, as I said, the result of interference. And this is also when the concept of being in phase is relevant, because the two waves need to be, well, they're not always in phase, but they at least need to have the same frequency if you're going to get a nice regular standing wave pattern like that. Standing waves are very important in music. We can show that much of the complicated behavior or sounds that we hear in music is actually a combination of some very basic principles of basically pitch, which corresponds to frequency, loudness, which corresponds to amplitude, and superposition of waves one on top of the other, producing standing waves in accordance with the principle of interference. But we'll talk about that in more detail when I do an episode on sound and music. Okay, so that's all I wanted to cover today. This podcast has already gone on longer than I had hoped. Hopefully that was relatively clear. If you have any suggestions about how to improve the podcast, or topics that you'd like to hear, or anything like that, or any other feedback, I'd be happy to hear from you. My email address is fods12@gmail.com. Thanks for listening, and I'll talk to you next time.